So I've drawn the diagram again here for better clarity. So we are talking about a torque versus theta diagram, and the area under the torque diagram is work, as work is equal to torque into theta. So the actual work will be determined by the actual torque line. So this is the actual torque line. So you can see from this figure the area, actual work will be area under actual torque line on the torque theta graph. So that from this graph you can see it is OFGHT, OFGHT, JKL and O, JKLO. So the total area under this one will be the actual work. Now you can see that for different period of time the work is varying. So from the crank movement from O to A, the work is OFA, triangle OFA. Then from A to B it is AFGHB, that much area. The square FHBA. So like that for different portion of the three-theta diagram, the work is also varying. Now we have drawn here a mean torque line. So the mean work will be equal to area under mean torque line. So that is here EFHJLE. So because this line is cutting the actual work line at F, H, J and E. So if you want to calculate the fluctuating energy, so then you have to take the actual work or actual energy and subtract the mean energy. So anything fluctuating, if you want to calculate, you can just subtract the mean, you will get the fluctuating. So we will subtract this area E, F, H, J, L, E from the real work, then we will get this area that I will shade here. This shaded area is the fluctuating energy about the mean. So it is positive for some time and it is negative for some time. So that means about the energy, total energy fluctuates about the mean. It is above the mean sometimes and it is below the mean sometimes. If you average everything out, then the net work will be equal to the mean work. So that is the definition of the mean. So in this graph, the shaded area represents the fluctuating, represented by shaded graph in above picture. So as you can see from here, if this is the mean torque line, the portion of graph below the mean torque line will be supply of energy from the crankshaft. Let's say we are assuming constant torque supply to crank of mean torque line. So for some portion of the curve, let's say FGH, the actual energy is above the mean torque line. Actual torque is above the mean torque. So that time the engine will supply surplus energy. So for theta from A to B, real torque is above the mean torque. So hence the piston is supplying excess energy to crank. And similarly, if you look at some other portion, let's say O to A, In that portion, the real torque is less than the mean torque. So for O2A, real torque is less than mean torque. So in this case, the energy will be taken out from the shaft, from the crankshaft. So piston takes energy from crank because the mean real torque is less than the mean torque. If we are assuming this all, we are assuming constant torque supplied to the crank. The crank is having a constant load attached to it, and there is a constant torque applied on crank. So if the torque due to piston is less than the torque on the crank, then the crank will be driving the piston. If the piston torque is more than the torque on the crank, the piston will be driving the crank. In this case, particularly, you can see that there is no negative torque, still there is a fluctuation of energy. So that is because we have drawn a mean torque line, and the torque varies about the mean. So it is above the mean sometimes and below the mean sometimes. So you can see the portions for which it is below: OA for this portion, BP for this portion, BC for this portion, and BO. It is below the mean line. And for the portion F, A to B and C to D, it is above the mean torque line. So those are the positive energy input to the crank. So for calculating the fluctuating energy, we will take area of FGH, area FGH and area JKL. These are positive, and area OFE, area HPJ here, and area LEO here. So all these are negative energy. So let's say negative energy will show by some crosses like this maybe. So we can differentiate between the positive energy and the negative energy. The fluctuation of energy you can calculate by taking these areas. So the fluctuating energy will be the fluctuating energy is area FGH, area JKL, and then fluctuating negative energy is area OEF, PHJ, and OEL. These are negative energy. You can calculate the values of those, and from that you can get an idea of fluctuating energy for the flywheel calculation. Now, why the fluctuating energy is important for flywheel calculation? As you can see here, that for some portion of time from let's say A to B, the real torque is above the mean torque. So that time there will be surplus torque on the crankshaft, and the crankshaft will accelerate. So we will write here crank accelerates, and here in the portion B to C, the real torque is below the mean torque. So here the crank will be subjected to a negative torque, and the crank will be decelerating. So remember that crank is having is rotating at constant angular velocity. It is supposed to rotate at constant angular velocity omega, but due to the surplus torque or the deficit torque, it will keep on fluctuating. So let's say the mean speed of crankshaft, that is design speed of crankshaft, is omega, and due to surplus energy for some part of the crank cycle, the crank accelerates to omega 1, and then due to deficit energy from piston for some part of crank cycle, the crank decelerates, and say the minimum angular velocity into deceleration is omega 2. This is omega 1 is maximum angular velocity and minimum is angular velocity is omega 2. So omega 1 minus omega 2 is the fluctuation of the crankshaft RPM. So this is called the fluctuation of speed. So this is a quantity of interest. The fluctuation of speed you want to keep within some limits, and for that we keep the flywheel. So due to the inertia of the flywheel, the fluctuation is reduced. This will show in the derivation of the flywheel calculation. It is important for we are laying on a basic definition. The fluctuation of speed is defined for one cycle of engine revolution. So you have to consider complete 360-degree revolution. Maybe the diagram is symmetric about 180 degree. It is repeating after 180 degree, but you should consider the complete 360-degree rotation, and you can get the maximum and minimum omega and calculate the fluctuation of crankshaft speed. So now we consider the second case, that is the turning moment diagram for IC engine. Till now we considered for the steam engine, the turning moment diagram for a 4-stroke IC engine, internal combustion engine. The interesting thing in this case is that since the engine is 4-stroke, that means one stroke is equal to half revolution. If you remember the IC engine terminology, you have a piston inside a cylinder, and during first half of this is TDC, top dead center, and bottom dead center. So first half of the stroke is intake. The piston moves from TDC to BDC and sucks in the gases. So this is called the intake stroke. And then you have the second stroke where the piston moves from BDC to TDC. So this here the gases get compressed inside a chamber. So this is called a compression stroke. So in completing these two strokes, 360-degree rotation is complete. One revolution is complete in completing two strokes. And third stroke is the power stroke, where the combustion happens, the energy release happens, and the piston is pushed down from TDC to BDC. This is called power stroke. All the power is generated during this stroke, and this power is what supplies the energy for entire crank rotation. Whatever energy is taken during the compression stroke or the intake stroke, so power stroke supplies all the energy for that. And the final one is exhaust stroke, where the piston starts moving towards the top dead center from the BDC to TDC, and the exhaust gases are expelled out. So this is the exhaust stroke. So primarily the power stroke is only generator of energy, and rest all strokes take energy from crank. The exhaust, the compression, the intake, and power stroke is the only positive generator of energy. So here you can see that you have completed one revolution in intake and compression stroke, and one revolution in power and exhaust stroke. So you have completed two revolutions. So that's why you have completed two revolutions of crankshaft for one energy cycle. So for calculating the fluctuation of energy, we are interested in the energy cycle. So I'll try to draw a diagram here for the four-stroke turning moment. So remember that we are talking about torque on the crankshaft, so on the y-axis, and theta, the angular displacement of the crankshaft. This is 0 to 180 degree, then 360 degree, 540 degree, and then 720 degree. So you can consider two cycles for the construct. During the intake, what happens is that uh, you have to pull the air in. So there is negative pressure at the piston. Due to that negative pressure, the torque on the crankshaft is negative. Actual value is negative. This is zero value of torque. Actual value of torque is negative, and it is negative somewhere around 90 degree. The mid span of the intake stroke somewhere around here. And after the mid span, the inertia of the gases starts to create a positive pressure inside the chamber, and you get this portion, the positive forces on the crankshaft. Then from 180 degree to 360 degree, it is the compression stroke. 0 to 180 degree is intake. So during the compression, entire energy is taken from the crankshaft to compress the gases. So here the torque on the crankshaft will be negative. Energy will be taken from the crankshaft. Crankshaft will be decelerated. So 180 degree to 360 degree is complete negative energy, negative torque. Then after 360, the ignition happens and the high pressure rise happens in the cylinder. This is the main power stroke where the uh, crankshaft gets the torque. So this is the power stroke. And after power stroke, you have again negative torque on the crankshaft because you have to push the gases out. So the crank will be supplying energy to the gases. In the power stroke, the gases will be supplying energy to the piston. The piston will supply to the crank. But in the compression, the piston will supply to gases. Intake also, piston is pulling the gases. Exhaust also, piston is pushing the gases. So on all of these three, the torque on the crank will be negative. It will push the gases, so that's why it will be negative. And somewhere around 630, it will hit zero and then slightly positive due to the inlet valve opening up. So this is what the real picture will look like. So this is the exhaust stroke. Now in all these four strokes, the power generating is the power stroke, and these are all power consuming. As you can see here, the torque is negative on the crankshaft. Also, now if you want to calculate the fluctuation of energy for this system, you will draw a mean torque line. So let's say this is the mean torque line. The mean torque line is determined by taking the total energy of the system and divided by 2 pi. So total energy in one cycle divided by 2 pi, that is displacement in one cycle here, 2 pi. So the total energy will be the total area of graph, the net area. So net area here, let's say O, A, B, C, D, E, F, G, H, I, J, K, L, M, N. So you will take the entire area, you will take the negative area, A, B, C is negative area, E, F, G is negative area, K, L, M is negative area, and then you have some positive areas also, C, D, E is positive, and then G, I, J, K is positive. We'll take the net area. Here we define the mean torque. This also applies for the steam engine earlier. The mean torque is net area on T theta diagram divided by 2 pi for 4 stroke. For 2 stroke or a steam engine, it will be just 2 pi. And for the 4 stroke, it is 4 pi. So because you are having 2 pi for 2 stroke and 4 pi for 4 stroke. If you can define engine with higher number of strokes, it will be that number of pi. So the mean torque, also if you want to calculate the fluctuation of energy, you will draw the mean torque line like this, and then you will take the portion of the graph below the mean torque line. So everything below the mean torque line will be negative, even though C, D, E is having positive torque, but it is below the mean flow line. So everything below the mean flow line will be negative energy or negative work that will be taken from the crankshaft, and anything above the mean torque line will be positive work that will be given to the crankshaft. Now we'll consider another related topic in the turning moment diagram, that is turning moment diagram of multiple cylinder engine. So if you have multiple cylinder engine and if the multiple cylinders are spaced apart in the crank angle, they don't lie in the same crank angle, then you will have for each engine a different turning moment diagram on the crankshaft, and the net turning moment diagram for the crankshaft will be summation of those. So let's say I'll just ignore the small parts in the diagram that we have here for the four-stroke IC engine cycle, and just consider that it looks somewhat like this, a triangle like this, T theta diagram for a single cylinder. So I'm just taking the arbitrary example. Can be of the face can be anywhere, the triangle can line anywhere, the shape can be different. So just a general example. Let a single cylinder graph looks like this. So if the multiple cylinders are spaced apart in crank angle, then we are interested finally in the T theta diagram of the crank. So torque on crank shaft, the net, because multiple cylinder will look somewhat like this. So you will have different engines, they are connecting to the crank shaft. So the cranks are at different phases. So here the theta might be, let's say, 270 degree. Here the theta is 90 degree. Here the theta is 180 degree. So for different means different. But we'll have a single T theta diagram for the crankshaft. For that crankshaft, how the diagram will look like. So for we'll see the contribution from a single cylinder. We have drawn here. Let's say the single cylinder diagram was from 180 degree to 360 degree like this, and we have neglected a small portion. So it will look like this is 180 degree, this is 360 degree. So a single cylinder, which all due to a single cylinder will look like this. Now let's say the second cylinder is spaced 90 degree apart. Cylinder, let's say this is one cylinder number one, cylinder two, cylinder three. So let's say cylinder two is spaced, uh, like we will take whatever is written in this figure. So let's say cylinder 2 is spaced 180 degree apart from 1, and cylinder 3 is spaced 90 degree apart from 1. So you can see here when angle in 1 is 90 degree, the angle in 3 is 180 degree. So they are 90 degree apart in crank angle, and the cylinder 2 is 180 degree apart in crank angle. So if you this is the diagram for cylinder 1, then the diagram for cylinder 2 will be 180 degree shifted, and it will look like this. This will be the diagram for cylinder 2. So it will be 180 degree shifted. And how the diagram for cylinder 3 will look like? It is 90 degree shifted from 1, and also 90 degree shifted from 2. It will look like this. 70 degree, 90 degree. So the net turning moment diagram is of superimposition of turning moment diagram of all engines. There's a multiple engine cylinder, multiple cylinder engine. So all engine cylinders. So just superimpose that, you'll find this. Now there is a special interesting property here. If you consider the area under the graph, so we have to draw a mean torque line. So if you draw a mean torque line, you will observe that, uh, like I'll draw it here. This is a mean torque line, and you will observe that the portion below the mean torque line is considerably lesser than as what compared to my single cylinder case. So single cylinder, I would have drawn this line, so this much would have been the area below the mean torque line, and this much would be an area above the mean torque line. In the multiple cylinder, you can see only a small portion of area is above the mean portion line, and a small portion is below the mean portion line. So the fluctuation of energy reduces in a multiple cylinder configuration if they are spaced apart in the crank angle suitably. If all of them are in same phase angle in crankshaft, then this thing will not happen. If the simple superimposition is such that they are overlapping after some phase, so then the negative of one will be compensated by positive of the other. So here the negative of 1 or 2 is compensated by positive of 3, and similarly the negative of 3 is compensated by positive of 1. So the in multiple cylinder engine, the fluctuation of energy reduces considerably if if the multiple cylinders are spaced apart in crank angle judiciously. So just by doing this thing, you can reduce the fluctuation in energy, you can reduce the fluctuation in speed of the crankshaft, and you can reduce your flywheel sizing. You can go with a smaller flywheel. So hence the multiple cylinder is advantageous. Now we will do one final derivation about the fluctuation of energy. So let's say this is a general graph of the turning moment, and this is the mean line, and this is T-theta diagram of any general engine. This is the main line. So from this diagram, you can see I'll just label it. I'll just label the areas instead of naming the points. So let's say this area is A1, this area is A2, this area is A3, this area is A4, and this area is A5, and here the cycle ends. Let's say 2 pi or 4 pi, depending on the stroke of the engine. This may be 4 pi also. So here one cycle ends. So I'll just write a cycle to be more general. So one cycle. So here you can see if the E is the energy at the start of cycle. At start of cycle. So let's say this point is A, this is B, C, D, E, F. So at point A, the energy of the crankshaft will be E plus A1 because A1 area has been added. Now at point B, the energy at point A. Uh, the energy at point A is E, and energy at point B will be E plus A1, and energy at point C will be energy at point B plus energy minus the area A2. So E plus A1 minus A2, and then the at point D, the energy will be E plus A1 minus A2 plus A3. Similarly, at the point E, it will be E plus A1 minus A2 plus A3 minus A4, and at F it will be E plus A1 minus A2 plus A3 minus A4 plus A5. But the point F and the initial point A is same. So F endpoints of cycle. Endpoints of a cycle. So hence the energy at point A, that is E, will be energy at point F, that is E plus A1 minus A2 plus A3 minus A4 plus A5. So E and E will cancel out and we'll get A1 plus A3 plus A5 is equal to A2 plus A4. So hence you can see the A2 and A4 are negative energy, A1, A2, A3, A1, A3, A5 are positive energy. So sum of positive energy is equal to sum of negative energy.